Hi, everyone. Good morning. I see people, everybody is settling down, logging in. Welcome to this webinar. So the topic of this webinar is deploy advanced turnkey load balancing for Virtual Cloud Foundation, VCF. Now, we have been doing these webinars on a recurring basis every month, and we run these in different time zones. So thanks a lot for attending in whatever time zone you're all in. So when I mentioned VCF, right, the virtual cloud, the VMware Cloud Foundation, it enables a consistent and secure infrastructure and operations for enterprises. And all these enterprises, they have a hybrid cloud strategy, right? They deliver applications in hybrid cloud environments. And customers across the industries and verticals, they want that ability to scale or transparently move workloads between on-prem and public cloud, and broadening workload deployment, and those are the reasons they choose VMware Cloud Foundation. So I just have, so that's what the webinar is about. It's all action-packed, very exciting agenda. And I just have few housekeeping guidelines before I turn it to our speakers, Rahul and Gary, to begin their presentation, as well as the demo. This webinar is for 60 minutes long, and Rahul and Gary will be tag teaming to present, and the demo as well. Now, this session is being recorded, and I hope my audio is absolutely clear to all of you. You will get the recording as well as the slides in a follow-up email. So if you find the content really useful, please feel free to share it with your co-workers as well. And so those of your co-workers who are not able to make it this time, they will have the recording and they can make some value out of it. You can use the Q&A window to ask questions. So let's make it interactive. Any questions that you have, please place them on the Q&A window, and we'll help answer those while the webinar is going on. So without further ado, let me introduce you to Rahul and Gary, who will be kickstarting the webinar for us. Rahul, please take it away.
Thanks, Irby. Hey, folks. Good morning, good evening. I'm Rahul. I work for product management for Avi Networks, which was acquired by VMware last year with a vision to bring in enterprise-grade load balancing into the VMware fold. Now, let me introduce Gary Blake, who's with us from the VCF team, who's a solutions architect spearheading VCF deployments and VVD designs, solution architectures, reference architectures across the board. And Gary will help us give perspective on the VCF as a cloud operating model and the various deployments that Gary has seen. And then we'll talk about the load balancing challenges that are seen in the VCF deployments. And then we will contrast that with Avi being onboarded onto the VCF stack, and how we will try and solve some of the problems that enterprises are seeing today. We will also demo that with a live demo where we will showcase the resilient self-healing elastic fabric that Avi brings to the fold. And that will showcase essentially the platform and the application fabric resonating with the aim and sort of the vision to solve the sort of top priority pain points of our customers. So with that, let me hand off the baton to Gary, who will begin the proceedings.
Hi everyone. So Gary Blake, as mentioned, I'm a solution architect working within the VCF team. I've been at VMware for 9 years, held various roles, but been working alongside VCF and validated designs for the last 5 years. So let's get on with the presentation and the slides. So first of all, let's take a look at how the digital foundation enables you to build, run, manage, connect and protect your apps across any cloud and deliver them to any device. Most of you have probably seen this slide before, but any cloud, what this really means is, we want to give you the choice so you can operate whichever cloud environment best meets your needs, run your apps across hybrid, edge, public clouds whilst managing the complexity, cost, and security, and also take advantage of newer environments such as telco clouds and 5G. You can connect all of this, apps, clouds, data, and endpoints with software-defined networking, which helps provide the consistent platform across all these cloud types, applications, giving you greater scale and security. When we talk about any app, what we really mean here is the ability to build, run, and operate cloud and container-based applications faster than ever, drive costs out of your traditional environments, and connect your existing applications data sources with the new ones to create new ways of working. From any device point of view, this really boils down to flexibility and choice. Our vision and strategy is about empowering your employees to be able to use whichever device they want of their choice, but at the same time ensuring that we've got a secure digital workspace for them to consume. And all of your devices, applications, and data are protected with this proactive intrinsic security. And a great example of how this vision has truly come together in recent times. We're all under this unprecedented global pandemic status where time has become money. This vision and strategy from VMware, I think we found certainly has been a major contributor in helping our organizations deal with the challenges they've now faced, where they're having to shift from the traditional, office-based workforce out into this sort of this working from home remotely to help with the social distancing. So it's a great example of how this digital transformation has come about. Next slide, please, Raul. So let's take a little bit of a deeper dive into the sort of the traditional data center. And the bottom line here is that traditional data centers can't keep up with the speed of business. We talk about the any cloud. Clearly, we've got true cloud providers out there. We've got hybrid cloud, but we've got private clouds. And private clouds are where the traditional data center really sits. This typical data center provides a trusted, compliant services within your organizations. Right, the IT teams find it increasingly difficult to keep up. Systems become outdated or are outdated. Processes start to become a limiting factor to help drive IT ability. And as a result, the responsiveness to businesses' needs and demands is diminished. The complexity that exists in these environments is typically down to sort of hardware-centric, where we have, we're restricted in complexity of being able to move additions, changes in terms of patching and updates, and just general lifecycle management. This is complex, it's time-consuming, it's also disruptive. From an inefficiency perspective, being able to reduce that technical debt helps, reduce that technical debt around maintaining the infrastructure will actually free up resources for new projects and new directions. It's slow. Outdated systems, the processes, they just simply limit the IT's ability to be responsive to the business. They often consist of multiple silos of expensive purpose-built hardware. This can be underutilized and with little to no automation capability. And then from a compliance and security risk perspective, these environments have evolved traditionally over time. The ad hoc building of strapping new capabilities on is limiting the ability to implement consistent and robust governance and the controls which help us to reduce the risk to the business. But what customers really like about cloud is not necessarily cloud itself. I mean, we talk about here private cloud. They like the flexibility of the cloud operating model, which really boils down to simple, quick, agile, repurposable, and it doesn't involve upfront investment costs. VMware's built VMware Cloud Foundation to deliver on that digital foundation and this vision to address those challenges of the traditional data center. And through a turnkey private cloud platform, we're allowing customers to take advantage of this cloud operating model. So what is Cloud Foundation? Well, Cloud Foundation consists of workload domains. And the best way to describe or think about a workload domain is this application ready infrastructure. Each workload domain is considered its own self-contained compute capacity for customer application workloads. Each domain is purpose-built. It's a purpose-built unit of private cloud capacity that allows your admin staff to configure and manage independent units of infrastructure to support the different types of workloads that you're having to deal with. Each workload domain is essentially a dedicated resource. So you have your compute, storage, networking, and security that's inherently built into the Cloud Foundation platform. That's automatically deployed, configured using Cloud Foundation automation. So in this case, SDC Manager. And once the workload domain is operational, this allows the admin staff to leverage the VCF automation to be able to scale the domain up, down, as well as carry out ongoing lifecycle management tasks such as patching and upgrades. As we go through this deck, we'll start to discuss how Avi Load Balancer complements this strategy in terms of these desired characteristics. So if we take a next level look down, next slide please, Raul. If we actually peel back the workload domain types, what exists under the covers? Well, ultimately VCF is built up of a couple of domain types. So we have a management domain. So this is where all the management components that follow VMware best practice to separate out the customer workloads. So we deploy various components on the management domain. And then the workload domains become the dedicated customer resource. So when we do the initial deployment of VCF, which we refer to as bring up, that's the process where we build out the initial VCF infrastructure and those management components. This consists of a vCenter server, NSXT data center management cluster, that manages the domain itself, and the SDC Manager, which is the tool that provides the core logic and the user interface for your Cloud Foundation instance. Workload domains can be provisioned for a variety of different use cases. Each workload domain is comprised of one or more clusters, so vSphere clusters, and it can then be scaled and lifecycled independent of each other. For each workload domain, we also deploy a dedicated vCenter that encompasses the workload domain, and you have a choice around NSXT. It could be a dedicated ESXT data center management cluster, or it could be one that's shared across multiple workload domains. And we actually support today the ability to scale an instance of SDC Manager up to 14 workload domains. So workload domains utilize this standardized repeatable infrastructure, which allows you to move away from provisioning and managing separate silos of custom infrastructure components. They can be sized, they can be provisioned for whatever you need, and they can be scaled elastically when required, which helps to drive greater levels of density and utilization. Next slide. So in today's world, we have a world of applications. I mean, literally, you hear the phrase of, yep, there is an app for that. And ultimately, all applications really require load balancing in some shape or form. We have various kinds of applications such as, containerized workloads. There could be legacy applications. We have web applications. We also have services that require various needs when it comes to load balancing, such as the digital workspace, internal IT applications, B2B, B2C applications, and of course, 5G, always connected applications. So enterprises today are being asked to do all of this and more with less. They're being asked to increase the number of applications they're deploying, reduce the amount of time to the market, at the same time deploy these applications and do so in a more cost-effective way. Customers now have more applications, have a significant increase in the number of changes they need to handle, and as such, much increased diversity in where these applications are deployed. And that's where a truly policy-driven load balancing solution comes into play. Over to you, Raul.
Thanks, Gary. And based on this, what Gary mentioned, even on the VCF stack, which has really managed to bring together and streamline and truly operationalize compute, storage, and core networking, but enterprise-grade load balancers are yet to cross that bridge. Load balancing has become a very manual roadblock where businesses are still stuck with IT ticketing processes. This creates a couple of unique and considerable challenges for the enterprise. The platform doesn't scale. Scalability is a big problem. The load balancer real estate is deployed as active standby pairs, which are most typically over-provisioned. There is also a lack of capacity pooling because these run as silos. If an application is running hot on one of the active standby pairs, and there is existing capacity, available capacity on another active standby pair, it cannot be effectively pulled together. Also, because there are no reference architectures to deploy traditional load balancers on top of VCF, they pose interoperability and lifecycle challenges. And also, load balancing is deployed as a bolt-on rather than a unified solution. This creates inconsistent and unreliable operations and also multi-vendor support challenges. Load balancers, traditional load balancers, also often have partial or incomplete automation at best. There are no native integrations which help enterprises integrate with their IPAM, DNSs, PKI infrastructures, ecosystems, etc. Also, because of appliance sprawling with multiple active standby pairs deployed, they pose multiple management points, again causing operational headaches. Now, this at the end of the day will drive up TCO for the businesses. Disparate solutions will drive up capital expense, and lack of automation and self-service drive up the operations. And so even with all these great advancements that VCF brings with time to market, time to deploy, time to troubleshoot, essentially is remaining still the same, with load balancing being a bottleneck. What we are finding from customers is because load balancing is the last holdout to be automated, this is something that's becoming more and more critical for deploying production-ready applications. Now let us look at how Avi with VCF will help solve these problems. Before we talk of Avi on VCF, I'd like to give a quick primer on the Avi architecture. Avi was architected from the ground up with modern distributed SDN foundations that separate the control plane from the data plane. The Avi controller manages the lifecycle of the data plane, that is the Avi service engines. Avi controller is a configuration repository and a single point of consumption via first-class REST APIs. This is where the policy-driven approach comes in. The data plane is a horizontal, elastic, scalable fabric of load balancers. The Avi controller spins up Avi service engines, scales them out, scales them in, and also self-heals them if there is any failure. This truly brings together public cloud-like experience to the on-premise environments. This is what the vision of the cloud operating model is. As Avi is a pure software solution, it can be run anywhere. Bare metal, VMware, VMs, containers on any ecosystem, on-premise such as VMware, VMware with NSX, etc., or public cloud such as AWS, Azure, GCP, giving the same experience everywhere. Now, being in line with application traffic, Avi service engines ship critical network, application, and security telemetry to the Avi controller, which then provides valuable metrics and actionable insights. The platform is also built on the construct of decision automation. I'd like to spend a quick minute on describing what decision automation means and how it is truly a differentiating factor. Now, task scripting and decision automation is something that we like to compare, where task scripting is a great way to tackle point problems. Through scripts to perform a well-defined action, many products that provide APIs can be scripted, but the scope of what this can do is very limited. Building out intelligence to make effective changes in real time to deal with ever-changing real-world situations is something that cannot be achieved through this methodology. Whereas in contrast, Avi's platform is built on the fundamental notion of closed-loop intelligence, which is to have a continuous feedback loop which relentlessly tries to realize the intent of the configured applications. It constantly observes and collects rich telemetry, analyzes it to produce actionable insights, decides on what would be the best path to take based on those insights, and acts on those decisions, adjusting to application behavior and demand in real time. Now, Let's take a look at how the various value propositions that Avi brings to the table with enterprise-grade load balancing and how they complement what VCF's value propositions that were shown previously. Let's start with the deploying with one click. Now, based on the decision automation thought that we just saw, let's expand on that a little bit. Automation is more than just REST APIs and ecosystem integrations. Avi takes the analytics that is fed to the controller to achieve auto scaling and full lifecycle management. It allows users to just specify an intent for the application, and Avi does the automation and orchestration required to achieve the outcomes, which is to provision the virtual service or the application and make sure that the application KPIs are always met. What makes automation increasingly important is that it's the critical step to finally operationalizing digital transformation. That is going from vision to reality. Now, I'd like to describe essentially two elements that are part of this journey of automation. One is infrastructure automation, which means Avi controller can talk natively to APIs of vCenter, NSX, Azure, AWS, etc., with the aim to provide complete lifecycle management of the data plane. So if a user wishes to deploy an application, for example, in a VMware environment, the Avi controller will talk to vCenter, find the best location, the best host to deploy a new service engine, upload the service engine OVA image, then automatically deploy the service engine VM. It will then configure the NICs by placing the service engine VM on the right networks, and configure the application on the service engine and take care of all of this for the user. Note, the user just said, I want to deploy this application into a VMware environment and nothing more. On the second hand, with operational automation, as Avi is not an island of technology, it needs to integrate with other pieces of technology and infrastructure in the data center. Operational automation aids in delivering this, which truly completes end-to-end automation. For example, by automatically configuring a VIP, by talking to Infoblox or another IPAM, or automatically registering the virtual services VIP into DNS by talking to something like Amazon's Route 53, or talking to Venafi for certificate management. The point is that by integrating with these surrounding ecosystems, it enables the application owner to simply convey the intent of the application and it just works. How it worked, they don't really need to know. They don't really need to care. Now with that, let's take an example of a simple action of creating a virtual service and contrast that between how a traditional load balancer would achieve it versus how one would do it on Avi. Now, without Avi, to provision a virtual service, it can take from days to weeks because admins have to figure out whether load balancers exist, whether they are in the correct environment, what are the performance requirements, figure out all the dependencies. And while those dependencies are being figured out, there are still ticketing processes that go across infra teams, application teams, etc. There is manual planning required for capacity management, etc. And this ultimately causes delays. When finally the load balancers are ready to be provisioned, they still need to be configured. They need to be configured and inserted into the infrastructure where firewalling, routing, etc. policies need to be configured. Post that, the application can be configured on the load balancer. And this delay, this ticketing process, the roadblocks that exist ultimately cause problems to businesses. Business outcomes essentially suffer. As a contrast, with Avi, like we mentioned, with the policy-driven infrastructure, with the intent realization architecture of Avi, all that a user has to do is declare the virtual service attributes. They just need to say, hey, I want to provision an application in my VMware environment. Avi controller then takes care of the grunt work of all of those ticketing items, all of the provisioning, capacity management, figuring out what VIP IP should be assigned by talking to an IPAM, configuring network interfaces, configuring security policies on the service engines, which are the load balancers, registering the VIP with the DNS. And after all of this is done and the application is stood up, Avi controller will continuously monitor performance of the application in real time and then take decisions on either to scale out or scale in the application, or even in the event of a failure to make sure that the service does not degrade. All of this is done for the customer with essentially a click of a button or an API call. And this is incredibly powerful. The second point that I'd like to highlight is the truly infinite scalable elastic fabric. The picture that is shown here showcases Avi controller having a fleet of Avi service engines, and the rectangular boxes showcasing applications that are hosted on those service engines. Avi controller is also a fully tenant solution, where the picture here is showcasing tenant 1 and tenant 2, which are separated both in terms of control plane, which is configuration, as well as the data plane, which are the hosted service engines. Also, the service engines are deployed in an active HA mode. What that means is every application is being serviced by 2 or more Avi service engines at the same time. Now, if for whatever reason a service engine fails, Avi controller automatically detects that and will make sure that the capacity that was required by the applications hosted on that service engine are serviced. Avi controller will automatically move the applications to existing service engines and also create additional service engines if required, and also rebalance the applications if there is a need for that. The outcome of this essentially is that the end perceived service disruption is 0 to minimal, because there is already an active fabric servicing the application. And if for whatever reason, if there is a failure, Avi controller handles the redistribution of the applications and reprovisioning of load balancers instantaneously. Now, as a contrast with traditional load balancing schema, there are 2 models in how customers typically deploy. One model is to deploy fewer load balancer pairs, which are large in size, which compact a lot of applications. In that scenario, if one load balancer fails, then a lot of applications have to cut over, and a lot of applications perceive service disruption. The other model is to deploy a large fleet of smaller load balancer pairs with fewer apps deployed on each. Now, the problem with this, even though the blast radius is smaller, the problem with this is that there is appliance crawling and there are a lot more points of management. With Avi, because of the centralized control plane and the resilient self-healing fabric, customers have the choice to deploy either large or small load balancer, even per application load balancers if necessary. But the same resiliency and self-healing applies to the entire load balancing fleet. And the customers can really make the choice of how they want to deploy without worrying about the operational hassles. The other aspect of scalability that we'd like to highlight is the auto-scaling nature of the load balancing fabric. The controller is constantly analyzing application telemetry in real time and takes decisions to either scale out or scale in capacity. What this means is there's no need to do holiday bursts planning. There is no need for capacity planning. If an application requires more load balancing capacity, Avi controller will gauge that based on the KPIs that are set by the user, such as connections per second, packets per second, CPU consumed on the load balancers, etc. And whenever these KPIs are exceeded, Avi controller will gauge that and automatically create excess capacity and scale out the application. Also, when the capacity is no longer needed, Avi controller will take out the excess capacity that is created and thereby saving costs for the customers, where they don't need to have an over-provisioned fleet of load balancers pre-created. Another important aspect of managing the load balancing stack and the load balancing fabric is lifecycle management. Avi has a key advantage with a centralized control plane, which helps orchestrate, upgrade, and lifecycle management in general for the entire fleet of load balancers. The picture that is depicted here showcases that Avi controller is deployed with 3 tenants. Tenant 2 and tenant 3 are deployed in data centers on premise, and tenant 1 is deployed in the cloud. There are applications that are running across the board. What Avi controller facilitates is Avi controller is the one that orchestrates lifecycle management and upgrades for the entire LB fabric. Upgrades are done in a rolling fashion with careful orchestration. What that means is Avi controller makes sure that the services that are placed on the service engines load balancing fleet see zero application disruption. And this is done by carefully orchestrating the upgrades between each load balancer resource pools, which are known as service engine groups, where a service engine is upgraded such that the applications are moved and replaced to essentially deliver zero application disruption. Avi also provides flexibility to upgrade only certain lines of businesses or only certain resource pools. Resource pools essentially are known as service engine groups, which host the service engines within them. And this offers lines of businesses great flexibility, where they can decide that the entire tenant needs to be upgraded, or even within a tenant, only certain resource pools need to be upgraded. This offers great flexibility. Avi also offers rollback and patches, which are meant for hot fixes. Now, this makes Avi LCM incredibly powerful and operationally super simple to use. Now, with Avi and VCF together, with VCF onboarding Avi onto its platform, it truly helps unlock full digital transformation. From challenges, we go to benefits, where the elastic load balancing fabric effectively is infinitely scalable. It is an active fabric where applications are deployed on a fleet of service engines and not in an active standby nature. There is centralized capacity pooling handled automatically by the Avi controller. There is no need for over provisioning because Avi controller handles capacity management. With Avi part of VCF, with reference architectures, VMware validated design documents, and integration with VCF, it's a VMware validated solution. It will simplify data center lifecycle management and will also provide for a single vendor support. This effectively helps deliver a unified data center solution for customers all the way from compute, storage, network, and also load balancing, which will connect from the platform infrastructure to the applications. Avi also provides a central automation platform for the application fabric. This allows for end-to-end application lifecycle management right from the platform to load balancer for any application on any cloud. Avi provides native integrations with the broader VMware ecosystem, including vCenter, NSX, Tanzu, etc. Avi provides elastic capacity management and also is self-service ready. Now with this, TCO considerably comes down because of a unified solution help driving CapEx, and automation and self-service help lowering OpEx. This effectively allows for infrastructure to service applications and businesses and not the other way. Now with that, let's take a quick look at a demo. In this demo, what we'll showcase is how Avi is deployed within the VCF stack, showcase the active load balancing application fabric. We'll show how auto scaling of load balancers is achieved, as well as failure recovery. So let me switch to my demo and quickly walk through the various entities that have been deployed. All right. We'll start with the SDDC manager, where SDDC manager is showcasing two workload domains that have been set up. One workload domain is the default management workload domain, and then there is a compute VI workload domain that has been set up. Each domain has a bunch of ESX hosts and also has been set up with NSXT. This environment is a VCF 4.1 environment. Looking at the vCenter, we see that there are a bunch of hosts that are provisioned, and there are a bunch of VM folders that have been created. We'll keep a lookout for the Avi SE folder in a bit. This vCenter is being managed by the NSX instance shown here, where we have deployed a T0 router, and to this T0 router, we have connected a T1 router. This T1 router has a bunch of overlay segments that are connected to the T1 router. I'm going to be using the SE management logical segment for the service engines, Avi service engines management NIC. I'm also going to be using SE data 1 as Avi service engines data NIC, which will actually participate in the load balance traffic. Now coming to Avi, we see there is a NSXT cloud that has been created. This cloud connector will allow Avi controller to enable full lifecycle management of the load balancing fleet, as well as the application lifecycle management. Let's quickly take a look at the configuration of this cloud. In this NSXT cloud, we have connected it to the NSX instance with the NSX credentials. We have configured the overlay transport zone, which defines our virtual cloud. As mentioned, we are using the SE management connected to the T1 as the management network interface. And then we've added a couple of placement networks. SE data 1, which is tied to the SFO tier 0, and another SE data 1, which is connected to the second tier 1, has been configured in the cloud. We've also added the vCenter that this NSX is managing as the placement entity. This is where the Avi service engines would be created. Avi's cloud connector will talk to both NSX as well as vCenter to perform the required operations. It will talk to vCenter to host the Avi service engine image and then create the virtual machines and attach them to the right networks. It will talk to NSX to program NS groups and static routes for virtual services that are configured. And we'll showcase that in just a moment. Within the cloud, there is a construct of a service engine group, which is effectively a resource pool. Within each service engine group, customer can define how large or how small the service engine should be. This is the capacity planning that a customer can do, which is just one time. They set up the size as a cookie cutter size, and then Avi controller automates provisioning of the service engines. In the advanced section, customers can also choose and scope out where the service engines should be deployed. For simplicity, right now we've said deployed on any host that is available. We will also place the service engines in the Avi SE folder within the vCenter, which is shown here. Also, we are saying that any service engines that are unused, please delete them after 2 minutes of not being used. This will free up licensing. This will free up the load balancing, excess load balancing capacity that is unused on the Avi platform. Now going to the application space, what we see here is that there is a WAF application that has been created, which is an SSL application listening on port 443, which is talking to the WAF application pool, which has 3 backend pool members. Now this application is hosted on 2 service engines showcased here. And this is deployed in an active fashion, meaning both of these service engines are handling traffic for this application actively. Now let's go in to the application and look at some of the analytics data. And while we look at the analytics data, let me quickly ramp up traffic on this application so that we see the true nature, the nature of how auto scaling of the load balancer fleet works. The picture that we show here right now the application is running on 2 Avi service engines. And in the infrastructure side, we only have 2 Avi service engines created in the NSXT cloud. Now with that, let me go ahead and quickly ramp up traffic. What we should see happen is that the traffic for this application should shoot up. And when it shoots up, we will see that the Avi controller will figure out that the performance requirements, the KPIs that have been defined have been breached. And I have set up performance requirements of CPU anything above 75% needs excess load balancing capacity. What we can see from the service engine is that it was running at about 50%, but it has breached the 75% boundary, and it's running right now. It's running hot at 87%. Soon as the controller detects that the KPI has been breached, it will detect that there is a need for excess load balancing capacity. While that is in play, let's quickly take a look at what this screen is telling us. We are looking at the application dashboard, and the application dashboard is showing us end-to-end timing. Hovering over a data point here, it shows that the latency profile for the application more or less has been constant thus far, meaning the total latency on average is about 3.3 milliseconds, with client RTT, server RTT, application response, and data transfer clearly split out. Now, what happened when we increased the load is that the existing service engines were unable to handle the load that was sent to it. The latency jumped from about 3 milliseconds to right now at about 8 milliseconds, with both client RTT and server RTT jumping. We do have more requests that are being serviced, but the application, the client performance is suffering at the moment. But what has happened is that moments after the traffic went up, Avi controller detected that the capacity required for this application was no longer sufficient, and it issued a scale out. Scale out for this application, meaning it needs another service engine. That triggered a creating service engine event. This service engine VM, Avi SE YWCFI, would be instantiated in the Avi SE folder. This is the new service engine that has come in, and we see some of the events in the task here, where we say deploying of the service engine VM is happening. We will also see that the service engine now is initializing in the infrastructure, which will soon connect up to the controller and then will host the WAF application. Once that happens, we will see not only the request rate going up, but we will also see that the end-to-end timing will start coming down because additional load balancing capacity has been added, and the nature of the active-active fabric will allow the load to be evenly distributed between the three. The way the load is distributed between the three in an NSX environment is by creating a static route on the tier 1 to attract traffic to all the service engines that are servicing traffic. Based on the application, we have placed the application on the SFO tier 0 from the virtual service configuration. And the VIP for the service engine is 400.100.101. Looking at the NSX T1 SFOM01, we see that there are a couple of static routes that have been injected. Looking at the static route, we see that this demo VSWIP WAF application has been created. This has been created by the controller by talking to NSXT APIs. Looking at the next hops for the VIP, which is 4.100.100.101, which is the VIP IP on the Avi controller, we see that the next hops programmed are 2 next hops, which are the data interfaces of the 2 service engines that are currently deployed. So if we look at one of them, for example, we will see that one of the IP is 172.101.25, which is this guy, and the other IP would be of the other service engine that is currently servicing traffic. Now, what should happen is as soon as the application is placed on the new service engine, which is this guy, YWCFI, we should see a new static route being injected into NSX, thereby attracting and distributing traffic not to 2 entities, but to 3 entities. If I hit refresh, there we go. And now we have 3 entities as 3 next hops, which are equally servicing traffic for the application. Now, if we go back to the service engine, to the application page, we saw the rebalance, which detected the KPI exceeding, which caused creating of the service engine. Then we see the service engine got created, and finally the service engine got added to this virtual service, and the scale out is complete. At this point, we should see all 3 service engines part of this application, which are servicing traffic for this application. With that, we will see that the performance that is being handled by the application or for the application has increased. And also we start seeing that the end-to-end latency profile has started to come down. Now, Avi controller will continuously do this in a feedback loop, continuous tight feedback loop, which we talked about in the decision automation. Now, what we see here is that still the existing, even though a new load balancer was added, the CPU utilization still hasn't gone below the threshold that we have set. Because of that reason, Avi controller issued another scale out, which causes another load balancer to be created. And now we're seeing that the 4th load balancer is currently being deployed by the Avi controller. Now, when this load balancer attaches and comes online, the same effect will happen, where a 4th load balancer would be added to the active fleet. Now, the number of load balancers can be limited by the service engine group configuration, which is seen in the advanced page, where I have configured a maximum of 4 load balancers or Avi service engines should be handling traffic for this virtual service. Now, while the traffic was running, I noticed that there have been certain percentage, about 20% of request errors. Now, the key point that I want to showcase here is that the application analytics window is an easy vehicle to figure out if there are any application problems. Just like we saw that there is a end-to-end latency problem here, looking at the request page, we quickly find out that there are request errors that are happening. When we look at the connections, we see that there are no connection errors happening. That means that from a TCP standpoint, this web application is fine. But when it comes to web applications or HTTP requests, there have been failures, and there have been considerable amount of failures that have been happening. Let's take a deeper look at that. And I would like to introduce the Avi analytics with respect to the log analytics that is packaged as part of the solution, where Avi showcases and collects application traces, and it categorizes application traces into significant and non-significant logs. Non-significant logs are all the 200 OKs of the world, where operators don't really need to bother. Those are all the traces which depict smooth functioning of the application. Significant logs, however, are logs and traces of interest, where they are errors, they are logs and traces that are causing excessive latency, etc. Looking at the application traces, what we see are a few things. Let's first, before digging deeper into the analytics and trying to figure out what the request errors are, let's quickly spend a minute looking at one of the trace. What we see here is we have a clear depiction of where the client is coming from, what browser is he using, what SSL certificate was negotiated, what VIP was hit, what server was picked. and also what service engine is servicing this traffic. Every request gets a request ID, and this can be used for features such as ICAP, etc., request parking, etc. Also, we noticed that the client made a request for b.html and did a GET request using HTTP 1.0. I'm just using a traffic generator for the demo purpose. Looking at the view all headers for each transaction that is sampled, we see the headers that are received from the client, the headers that the service engine sent to the server, and we could see the X forwarded for inserted so that the servers have an idea of what the client IP is. The headers that were received from the server, and then what was sent to the client. This is incredibly powerful. But having all this data is one thing, but allowing us to troubleshoot that and pinpoint problems without the need to actually doing TCP dumps is where value is at. Now we noticed that there were about 20% of request errors that were happening. So let's quickly see what significance tells us. Now looking at the significance, it is telling us that about 100% of the logs that have been significant, there are about 8% of them which have a WAF match. So let's see what that WAF match is. We're seeing that the WAF, almost all of them are doing a post and getting a response code of 405. Looking at the WAF rules that were hit, we see that there is SQL injection happening. So the logs that we see here are all SQL injection, and there is SQL injection happening from certain clients coming in. Also, we also noticed that there were response codes that were 4xx. Looking at the 4xx response codes, let's filter further down and see what all response codes are being hit. We noticed the 405 was the SQL injection that was happening. Now let's take a look at the 404 and what is causing 404s. 404s are URL not found, and it looks like there's a spread of URLs that is being requested. Let's take a look at if there is any pattern in the URL path. It looks pretty even with A and B.html, so it's not the URL or any particular URL that is missing. Let's figure out if any service engines are misbehaving. And it looks like they are spread across the service engines that are servicing this application. So ultimately, let's see if there is any upstream server which is misconfigured and is missing any of these URLs. And what we see here, what we see here is we quickly see that there is one server which is misbehaving, which is not configured with the A.html and the B.html resources. What this demo showcases is that whenever a problem happens in the legacy world, application admins would have complained that their application is suffering and they are seeing request errors. And then load balancer and the network admins would have gone ahead and use tools such as TCP dumps, etc., to really figure out where the problem exists, which is very tedious. And with this exercise, with the rich analytics as well as the application traces, it's really taking away trouble from the whole troubleshooting exercise. Now, going back to the application analytics, we see that the fourth service engine came in while we were looking at the analytics, and we went over north of 1100 requests at about 852, and about 852, the latency profile also was going down. After that point, we saw that the application performance requirement went down, and when that happened, the auto rebalance engine scaled back in, where it went from 3 load balancers to only from 4 load balancers to only 3, because the fourth one was no longer necessary. This showcases both the elastic fabric nature, which is scaling out when needed and scaling in when excess capacity is no longer desired. Now let me quickly show you how Avi enables self-healing aspect as well. And to do that, let me go to the service engine tab and pick a service engine that is available. Let me log in to service engine, or let me pick the first service engine. Let me log in to the HMZNX service engine, and I'm going to cause a failure of the service engine. What this should do is it should cause the application that is hosted on HMZNX to be placed on an existing service engine. So let me quickly do that. We will see this service engine going down and then the application being redistributed. I just caused a failure. And you saw that just in an instance when it was detected down, the application was replaced on existing load balancers. If existing load balancing capacity was not available, Avi controller would have done the same exercise of creating new capacity, more capacity for the load balancer. And here we see that an event just happened where a VS switched over, where the service engine was removed, the failed service engine was removed, and the new service engine was added. Let me go back to our demo and quickly summarize what we just saw. Now, by looking at the Avi Elastic Load Balancing Fabric that is part of VCF, and we will soon have Avi part of the VCF stack with Avi controller being integrated into the VCF solution, we will see that not only does VCF provide a scalable infrastructure platform for compute storage network, but now it will provide a scalable platform for applications as well, which is truly infinitely scalable, both in terms of the infrastructure and applications. Surabhi, would you like to take over and showcase how customers can engage and take the next steps?
Yeah, thanks, Rahul. Thanks, Gary. I know we are very close to 9 o'clock finishing it, but if we have any questions, please feel free to ask in the Q&A panel. So this is a great way to, if the customers want to build a private cloud, and we all know that VMware Cloud Foundation is becoming like the new vSphere. So if you are wondering how you can implement software-defined load balancing or application services and features like auto scaling, I think this presentation and demo has been very helpful. Is this, I have a question though, is this integration out there, or the release is already available? What is, or is this something, do you want to cover that a little bit?
Sure, Surabhi. The integration with VCF stack is in the planning, is in the works, and is in the roadmap. And watch this space. We'll be making announcements soon. It's on our roadmap.
All right, that's great. So if everybody, if you can go to the engagement slide, Rahul, again.
Yes.
So if you have any, you can go on the avinetworks.com/docs to see the recorded webinars over there. And we hold these virtual workshops and hands-on labs as well every month. You can register for those. And there are some pre-recorded ones that are available there as well. So we have good resources on our website. With that, thank you very much, Rahul and Gary, for the webinar, and thanks everybody for attending.